These are the answers to the second set of problems for Chapter 7, the additional student problems. This is really problems 7 through 12. 1 through 6 were done in the first video. Problem number 7, for nitrous acid, HNO2, they give us the Ka, and we are to calculate the pH of a 0.25 molar solution of HNO2, nitrous acid. All right, nitrous acid's a weak acid. And because it's a weak acid, we can set up an equilibrium reaction, and then we can use a rice box approach to get our answer. So R is reaction. We write our reaction, give ourselves kind of lots of room here. HNO2 plus H2O is in an equilibrium reaction to give H3O plus and NO2 minus. All right, our initial conditions, 0.25 molar of HNO2 and none of the H3O and NO2 minus. And of course, water, we leave it out. What is the change? Well, we don't know how much HNO2 dissociates, so that's going to be a minus X. And because the stoichiometry is 1-to-1, very easy, excuse me, we get positive X for hydronium ion and nitrite. So our equilibrium concentrations would be 0.25 minus X and X and X. So now we set up our equilibrium reaction, and we get 4.0 times 10 to the minus fourth is equal to X squared, X times X, divided by 0.25 minus X. Now, our Ka is not very small. And so I just don't think we're going to be able to assume that X is less than 0.0005. It's got to be significant digit-wise. It's got to be so far less than 0.25 that it's irrelevant to 0.25. And the only way to do that is to say X is less than 0.0005. And that's just not going to happen with 4e to the minus fourth. We would make an assumption. We would solve for X. We would see that our assumption is either invalid or only just barely valid. Really, it's just going to be less time consuming to just go ahead and solve the quadratic. Yeah, it's a little bit of a pain, but we can solve the quadratic pretty easily. And we're going to get X is 0.009802. Now, that's X, but X represents H3O plus. So now that I know X, I know H3O plus, I can take the pH by taking the negative, I can calculate the pH by taking the negative logarithm of that number, and I get 2.008. And of course, we're going to round that, look at our 4 or 5 available answers. We see that answer A is the correct answer. All right, number 8. We determine the molarity of a solution of the weak acid HClO2, which is chlorous acid. Again, the Ka is pretty big. It's just 0.0110 if it has a pH of 1.25. Okay, this is the opposite of the problem we just worked. Okay, since the pH is 1.25, which is fairly acidic, which makes sense because the Ka is pretty big, we know that H plus is just going to be 10 raised to the negative pH, which is 0.05623. Okay, now chlorous acid's a weak acid because it's not on our list of strong acids, and they give us a Ka. So we can write an equilibrium reaction and use a rice box. There's our reaction. Our initial conditions, X, 0, and 0. What happens? What do I get now for my change? Well, my change, I know I'm producing 0.05623, and I know that because I know the pH. If I know the pH, I know the H plus. And because of stoichiometry, if I know H3O plus, I know ClO2 minus has to be the same. Stoichiometry says it is. And that must mean that I've lost that much of HClO2. All right, so now I have an equilibrium set up. I have x minus 0.05623 on the left side and 0.05623 for each of the two products. And now, if I can write my equilibrium expression, 1.1 times 10 to the minus second is 0.05623 squared divided by x minus 0.05623. And I'm looking for x, the molarity of HClO2. So I can rearrange this, got to do a little algebra. It's not difficult, and I'm going to get 0.34371. Now I look at my possible answers, and I see that answer A is the correct answer. Number 9, in a solution prepared by dissolving 0.1 mole of propionic acid in enough water to make a liter of solution, the pH is 1.35. Now in this problem, we're asked to find Ka. Now we would expect Ka to be not small, right? pH is pretty low. So I'm pretty confident D is not the right answer, but I got to do a computation to determine if it's A, B, C, or perhaps E, right? So I can solve for the H plus concentration by taking 10 to the negative pH. I get my number. I set up my rice box. There's my reaction. My initial concentrations, 0.1 mole in 1 liter, that's 0.1 molar, 0 and 0 for the other guys before the dissociation. My change is, this is just like the last problem, except now, instead of solving for x, the initial concentration, I'm solving for K. Okay, so it's really kind of straightforward. In fact, it's really kind of easier. So K is just 0.04467 squared divided by 0.1 minus 0.04467, and I do that calculation. I get 0.036, which is 3.6 times 10 to the minus second. I look at my list of possible answers, and I can see that answer B is my correct answer. Moving on to number 10. Morphine is a weak base when added to water. The reaction produces 1 mole of hydroxide ions for every mole of morphine that dissolves, and they give us the Kb. So now they're asking what's the pH of a 0.005 molar solution of morphine. All right, so let's see if we can set this up. We don't really know the chemical formula for morphine, but that's okay. It's an equilibrium reaction because it's a weak base. We use our rice box, right? And I'm just going to abbreviate MOR-OH. That's morphine as a weak base. So I put it in water. I lose the OH minus, and I'm left with morphine plus and OH minus as my base. My initial concentration, 0.005, 0 for morphine plus and OH minus. I have minus X dissolving, giving me plus X and plus X. I know that because the problem description says I get 1 mole of hydroxide for every 1 mole of morphine. So now I have my equilibrium expression, and I can set up my rice equation. I know Kb is 1.6 times 10 to the minus 6, and that's going to be equal to x squared divided by 0.005 minus x. Now, I'm not really sure if my assumption here is going to work. So let's assume it. Let's check and let's see. I can ignore x with regards to 0.005. So now I end up taking the square root of the product of 0.005 times 1.6 times 10 to the minus 6, and I get 8.94 times 10 to the minus 5th. Okay, that is quite a bit smaller than 0.0005. My assumption is legit. That gives me OH minus, which therefore it's pretty easy to get POH. I take the negative logarithm of 8.94 times 10 to the minus 5th, but I want pH, not POH, so I subtract that from 14, and I get 9.95, which is answer B. All right, now we go to number 11. Calculate the percentage of pyridine that forms pyridinium ion in a 0.1 molar aqueous solution of pyridine, and they give us the Kb. It's pretty small. All right, so percentage of pyridine, this is not something we've done, but again, it's an equilibrium problem. Let's see if we can set this up using our ever popular rice box. We know the formula for pyridine. We get a pyridinium ion and an OH minus. We know that I have 0.1 to begin with. We know the change is minus X and plus X. So I have an equilibrium condition. And I can assume, because Kb is pretty small, I only have to assume X is less than 0.05, which would be so small that it would be insignificant compared to 0.1. So I'm pretty sure we can make this assumption. I solve, I get 1.3 times 10 to the minus fifth. Assumption is good. Now, to get the percentage that forms the ion, we divide by the starting molarity, and then I convert to a percentage by multiplying by 100. And when I do that, I get 0.013%. So I have 1.3 times 10 to the minus fifth divided by 0.1, my starting molarity, and then multiply that by 100, and I get that my answer answer E is the correct answer. Now we have one more problem to do. Let's see if we can knock this out. Okay, number 12. A 0.1 mole sample of a diprotic acid, H2A, is dissolved in 250 mils of water. I've got Ka1 of this acid is 1 times 10 to the minus fifth, and Ka2 is 1 times 10 to the minus 10th. Calculate the concentration of A2 minus in this solution. It's not a pH problem. Well, I mean, it's an equilibrium problem, but we don't have to calculate pH, okay? All we have to do is calculate the concentration of A2 minus. So because this is diprotic, we have two dissociations. Let's do the first one. So there's our first reaction. H2A plus water gives HA minus plus H plus. I know my initial concentration is 0.4. I get that because I have 0.1 mole dissolved in 0.250 liters. So my initial concentration is 0.4, and I have 0 and 0. Again, don't know how much I'm going to lose. That's going to be minus X and plus X. So I have my equilibrium concentrations. I see if I can make a simplifying assumption. I think it's going to be close, but I might be able to do it. We say that Ka1 is 1 times 10 to the minus fifth, and that's equal to X squared, X times X, divided by 0.4 minus X. Okay, I get X is 0.002. This is a valid assumption. It's close, but it's valid. So that's both the H plus and the HA minus. And I can use this to solve the second stage of the problem, which is finding A2 minus. I don't have that in my first reaction, but I can get that. Okay, so I've left the problem statement there. Now we do our second reaction. HA minus plus water goes to form A2 minus plus H plus. I had 0.002 of HA minus from the previous the first stage of this problem. I also had 0.002 of H plus, okay, minus X plus X. I get my equilibrium. So now I have Ka2 is 1 times 10 to the minus 10th is X times 0.002 plus X divided by 0.002 minus X. And I'm going to make another simplifying assumption because Ka2 is pretty darn small. And when I do, I get X is 1 times 10 to the minus 10th. And since that's the value of A2 that I'm looking for, I'm done with this problem. Answer D is correct. and we finished all the problems.